Lifting 80 tons of metal and passengers to 30,000 feet requires extreme energy density. Heavy batteries cannot support commercial long-haul flight. Liquid fuel is a physical requirement for the energy density needed. This constraint makes aviation one of the most stubborn sectors in the global economy to clear of carbon. This split-screen visualization illustrates the problem. On the left, a rising curve represents historical emissions. As travel demand rises, carbon emissions track tightly alongside it. But the projection on the right breaks that pattern. It drops below zero, into negative territory. For decades, the aerospace industry focused purely on engine efficiency to burn less fuel. This negative projection relies on a completely different mechanism entirely. The long-term objective for sustainable flight moves away from simple emission reduction. Instead, it aims to transform the global fuel system into an active carbon sink. A jet engine combusts hydrocarbons. By the strict laws of thermodynamics, it will always emit carbon dioxide in flight. You cannot achieve a net negative result inside the turbine. To find the deficit, you have to look outside the aircraft and examine the global supply chain that creates the liquid fuel in the first place. Redesigning fuel systems allows flying to function as an instrument for atmospheric carbon removal. To accurately track where carbon enters and exits this system, engineers use a life cycle assessment. It is a rigorous mathematical accounting of every gram of carbon involved in producing and burning a fuel. This matrix represents the carbon ledger across 4 evolutionary phases of aviation fuel. We start on the left with conventional jet fuel. With conventional fuel, we extract carbon that has been locked in the Earth's crust for millions of years, process it, and combust it in the sky. It is a unidirectional flow, resulting in a net positive equation. Because this carbon originates from underground reserves, every flight adds new mass to the atmosphere. To avoid extracting fossil reserves, the industry developed intermediate solutions: sustainable aviation fuel, or SAF, and synthetic fuels. These methods harvest carbon that already exists on the surface. They extract it from agricultural biomass or capture it directly from industrial waste streams. Notice the shape of the flow. Carbon is taken from surface waste, burned in the engine, and released back into the air where it can be absorbed by the next crop cycle. It operates as a closed loop, netting out near zero. While a net zero equation halts the addition of new fossil carbon, climate models require absolute reductions in current atmospheric concentrations. Stopping the leak does not drain the tub. This raises a physical paradox. How can combusting millions of gallons of liquid fuel result in a mathematical deficit of carbon in the atmosphere? The answer lies in the 4th phase of aviation fuel, carbon negative. Look at the balance in this column. The process begins by removing a massive volume of carbon directly from the sky. Only a fraction of that volume is eventually released by the aircraft. For this mathematical inequality to hold, the system relies on a strict physical condition. The precise mass of carbon dioxide extracted from the atmosphere during fuel production must verifiably exceed the mass emitted from the tailpipe. To move past a neutral ledger, aviation must abandon both the extractive fossil model and the closed recycling loop. The supply chain itself must be engineered for remediation. Moving from the theoretical math of the ledger to physical reality requires building an entirely new industrial architecture. This system architecture diagram outlines the 4 major subsystems needed to synthesize carbon-negative hydrocarbon fuel from scratch. The first block is direct air capture, or DAC. Giant banks of industrial fans pull ambient air over chemical sorbents, actively trapping the CO2 molecules. Because CO2 makes up only about 0.04% of the atmosphere, these facilities must process millions of tons of air to secure the raw carbon mass required for fuel production. Next, that carbon must bond with hydrogen. We fill the second block with green hydrogen, produced by splitting liquid water into oxygen and hydrogen gas. This electrolysis relies on immense electrical currents. It is an energy-intensive process that must run without consuming any fossil fuels. Both of these extraction and splitting processes draw heavily from the third block, renewable electricity. This is the critical vulnerability of the entire operation. The energy backbone must be perfectly clean and massive in scale to keep the fan spinning and the electrolyzers firing. Life cycle assessments calculate embodied carbon, the greenhouse gases generated simply to run the machinery. If the power grids feeding the DAC facility or the hydrogen plant burn coal or natural gas, the embodied carbon exceeds the carbon captured. The math flips, the remediation is canceled, and the system fails. When powered exclusively by renewables, the raw inputs move to the fourth block, carbon utilization. Inside synthesis reactors, high heat and pressure force the captured atmospheric carbon and green hydrogen to bond. This reaction systematically constructs the energy-dense long-chain hydrocarbons needed to propel a commercial jet engine. Following the verified mass flow, a massive block of CO2 is pulled from the sky. It passes through synthesis, fuels the plane, and a much smaller block of CO2 is emitted from the tailpipe. The resulting fuel is a strictly industrial product. By applying immense renewable energy to atmospheric extraction, engineers construct a permanent carbon deficit. We can now consolidate that four-part architecture into a single operational unit, the fuel system boundary. This model accepts thermodynamic reality. The engine will always act as an emitter. The metric for success shifts to a total atmospheric carbon counter over the system. As the jet releases carbon locally, the global system counter drops. Because the fuel production boundary removes far more carbon than the aircraft requires for combustion, the localized emission is mathematically erased by the global extraction. Aviation will continue to be one of the most energy-hungry, fuel-dependent, and physically inflexible sectors in the modern global economy to decarbonize. This lack of flexibility creates a unique role for the industry in synthetic remediation. The industry's massive, inescapable demand for liquid fuel can be leveraged to fund and scale atmospheric repair. Since commercial aviation cannot easily switch to heavy battery power, it remains a guaranteed high-volume customer for carbon-negative fuel. This steady demand provides the capital flow required to construct and operate large-scale direct air capture facilities. By coupling direct air capture and green hydrogen, the global aviation supply chain transforms. It becomes a primary vehicle for atmospheric carbon removal, turning the sector into an environmental repair tool.